how can we kind of evaluate our queries for performance, like, you know, predict whether they'll be efficient or not, and decide where to put indexes. And it's more than just there's a filter on this column, so put an index on that column. Specifically, when it comes to joining, it starts to get a little more interesting. So we'll look at how the GBMS converts an SQL query into an actual executed operation that retrieves data. So SQL is the high-level specification, just like a high-level programming language, and then there's some compilation-like step that produces what's called a plan. The plan is kind of just fundamental database operations for how to retrieve information out. We don't ever really look at the deep, dark details of the plan. Well, we can, but we don't usually. But we are going to today. So the basic job is kind of like a compiler. First, you parse the input command, you know, figure out, like, is it even the right syntax? What are they looking for? Then once you've converted it into some kind of workable form, like an intermediate form, then it optimizes the plan and then executes it. So let's look at this translation process from SQL to a plan. Let's look at it in the context of relational algebra, because those are the basic operations that the DBMS thinks about. Okay, so before we kind of go any further, though, assume that there are no indexes, even like the primary index. Assume there's no primary index. We're going way back to fundamentals of just how do we convert an SQL query into a plan. Whether or not an index exists will affect how it optimizes and picks which plan to use. Okay, so let's just look at a simple query. On the chess database, say we want to find the names of all players with an LO less than 2,000. Okay, so select name from players where LO less than 2,000 is the SQL form. In relational algebra, there are two reasonable formulations for this. We could first do the first do the filter. So that's the select in relational algebra. So this top one is filtering first, then projecting. The bottom one is projecting first, then selecting. Okay? So it's kind of harder to see what's going on here when we're just looking at order of operations, but what this implies is that the innermost thing there is the thing that happens first. So another way to look at this is kind of a flow chart. So we take P, like the input relation, put it through a projection first, then through a selection, or put it through a selection first, then projection. Which one is faster? Or does it even matter? Yep.
The second one should be faster?
The one on the right should be faster. So the filter part, the LO less than 2,000, that is going to have to look at every row, no matter what. So in order to filter this, we're going to have to look at every row. Once we have filtered, though, now we have fewer rows, and then the projection part can look at fewer rows. So projection does not remove any rows. Projection only removes columns. So it's going to be faster to remove those columns if we're doing it on the already filtered list of rows versus the one on the left. We're going to be projecting out all these names that eventually we don't even care about because they then will eventually be filtered out afterwards. So this is basically the plan. The plan generator is going to generate these two plans, and then it's going to decide which one of them is likely to be faster. And in this case, it's easy, and it's not even a matter of likely. It's like the one on the right will be faster. So it would pick that one. But obviously, it gets a little more complicated than just this super simple query. Okay, so this was easy to decide which one is faster, but when you start doing joins and more complex filters and everything, it has to start kind of using a heuristic. Once it has a few reasonable plans, how does it know which one's going to be faster? Well, it has to make some assumptions. It has to know something about the tables, like how many rows are in this table, how many of them are likely to be within the filtered range, things like that. And those are all guesses, essentially. It's based on heuristics. Okay, so let's look at another one. Slightly more interesting query, because I have a join in here now. So select result from games G, join events E. And I'm just renaming them so that I can use G and E in a diagram that we'll see in a second. On G.eid equals E.eid. So that's basically a natural join. It's just joining on the column they have in common. And then I'm using this where date is exactly equal to March 5th, 2005. Okay, so basically I want to know, like, who won? Was it white or black that won for any of the games that were played on that date? So here is one possible plan. You take games and events and join them together based on that EID column. Okay, then you feed that temporary result. That'll be a new temporary table. You feed that into a selection. Remember, a relational algebra selection, which is a filter for that date. And then you feed that into the project to take the result out. So this is good in that it's doing the projection last. That's you usually want to do projection last. Here, are there any other options for any other plans you can think of to do this query? Exactly. So what if we move the selection part up, the filter part up? So filter out all of the events on that date, then join that with games, and then project out the result. Chances are there's only actually going to be one event on that date, or some small number of events on that date. And that's the kind of guess that the plan generator would have to make. It doesn't know how many there are, but it knows the range of dates. Like, it knows they go all the way back to 1995 and up to 2018 or something. And there are a lot of unique dates. So it probably knows that that filter is going to reduce that table way down. Then you have a much smaller join. So remember, a join, ignoring indexes, a join is essentially a multiplication. Every row in G times every row in E. If we can reduce E down to 1, then it's G times 1 instead of G times E.
So in a case like this, don't we know that the query on the right is at least less than or equal to the one on the left?
Yeah, in this case, this is another very easy choice for the plan generator to pick this one. Okay, so let's look at, kind of break this down with more details, actually. So let's say there are 1,000 rows in G, so 1,000 games, and 100 rows in E, and 5 of them on that date. So instead of 1, maybe there's 5. Okay, so here's the one on the left. How many rows do we have to touch in order to execute this plan? So the join is 1,000 times 100, 100,000. The result, pass that into date. The result of that join is it's still only going to be 1,000 rows because we're finding every game with an EID that matches some event EID. So even though it's 100,000 rows to compute that table, the result is going to be 1,000 rows. And then we project out the date, or sorry, select out the date. So we have to look at all 1,000 of those. And then that's going to filter it down to 5 left. And then we do a projection on just 5 rows. So total 101,005 versus this one. Filter first on the date. So we have to look at all 100 events to do that filter. But then we end up with just 5 events coming out of that. So 5 times 1,000 to compute the join, and then 5 to do the projection. So we end up with roughly 5,000 instead of roughly 100,000 rows touched. But this is actually not even the whole thing. Let's say I put an index on events.date. Now, computing this filtered out set of events where they all match the date, now I don't have to touch all 100 events. I touch very few of them. And even though I have that index, it doesn't help the one on the left to do that date filter, because there is no index on that temporary joined table. The index is on the original events table. It does not help with some temporary table because you don't know what's in there. There was no index built on that table. Okay? So even if there is no index, it's going to pick the one on the right. If there is an index, you might think, well, it doesn't matter because the index is going to help out the one on the left too. No, you can't even use the index for the one on the left because that's a temp table. Okay? Questions so far? So kind of just working through, like, what is the logic the plan generator is going to go through? It has all this information available to it. Roughly how many rows are there? Where are indexes and where are they likely to help? Okay. All right. So now what about a join? Well, we have a join here, actually. We have a join here, but how does it actually compute the join? I've always said the most basic way to do it is it's just a full cross product. So for every row in the table on the left, for every row in the table on the right. So that is the most basic way to do a join, and it's called a nested loop join. There are other kinds of joins, merge join and hash join, which can take advantage of, like, if you know certain things about the tables you're joining, like are they ordered in a certain way? We're only going to look at nested loop join, though, for today. This is the one MySQL is going to prefer first because it's more general purpose. It can join any 2 tables. And so here's, two relations, R and S. They have some key in common, K, so I can do a natural join on them. And then they have some other column, we don't care really what it is. This is basically going to turn into a nested for loop. That's why it's called a nested loop join. So for every row in R, for every row in S, check if those keys match. If they do, add it to the output. If not, then just keep going. So the algorithmic cost of this is trivial to compute. It's number of rows in R times number of rows in S. The actual cost, you have to remember that we're dealing with a lot of disk I/O. So the actual cost is more dependent on your disk, how big are these rows and how many of them fit in a page, how much memory does your machine have, and how many pages can it cache in memory at a time. So that starts to get a little more interesting to think about. So let's look at in terms of pages now. So I have R and S still, but I've kind of just removed the data from them and I've redrawn them in the context of pages. So every kind of slightly different shaded region in R is a page, and each page has 3 rows. Same thing for S. So in this diagram, R has 5 pages, 5 times 3 total rows, and S has 4 pages and 4 times 3 total rows. 3 pages, 3 rows per page. So let's assume that memory can hold, so memory is really small for some reason. Memory can hold 1 page from R and 1 page from S at a time. So it's going to pull in like the top page from R, and as it's looping through, it'll only hold 1 page of S. So as soon as it hits those first 3 rows, it'll have to then throw them away when it moves down to the next page. Okay, so let's look at, not in terms of number of row combinations, but let's look at number of pages loaded. Okay, so here's the first few steps of the nested loop join. We have to load the first page from R, and we load the first page from S, and then we can compare that first row in R to the first 3 rows in S. Okay, then we move down. We have to load the next page of S. So I have these counts here. I've loaded the R page once and the first 2 S pages once. That'll just keep going. We'll get down to the bottom. We'll have loaded all of the S pages. Okay. Now we move to the next row in R, which is not the next page. That row is still in the R page. But I have to come back up and reload the first page of S because I can only fit 2 pages at a time in memory. So essentially this is like a cache. The cache had to evict that line. I brought the line in earlier, but the cache is not big enough, so it got evicted when I had to move down. So I come back up, and now I have to reload that page. And same thing's going to happen for the rest of this pattern. And we're essentially going to load every page of S once per row in R. So 15 rows in R means I load every single one of those S pages 15 times. And I only have to load the R pages once because it's the one in the outside of the loop. It's the outer loop. Okay? So now instead of looking at number of row combinations, which is not as interesting, now I'm looking at number of pages loaded. P sub R is number of pages loaded for R. P sub S is number of pages loaded for S. So I have just PR on the R side, and I have number of rows in R times P sub S on the S side. Okay? Any questions? All right. So does this matter then? I had R on the outside and S on the inside. So the for loop looks like that. What if I swap them so that S is on the outside and R is on the inside? Computationally, it's equivalent. Functionally, it's equivalent. Does it make a difference? So computationally, they're the same. You know, A times B is equal to B times A. You can have the same number of row combinations. But in a database, so think of what is special about a database. Is this going to make a difference?
You're loading each page in R times the number of rows in S, which is smaller than each page in S times the number of rows in R.
So, right. So we are kind of rearranging how frequently pages get evicted and re-brought into memory. So let me actually add to this question a little more. I had the detail on there that only 2 pages could fit at a time. If that wasn't the case, if we could fit more pages at a time in memory, then would there ever be any difference between these 2 loop formations? And when would it make a difference? I'll tell you, the answer is yes, it does make a difference. So when?
If all of one of these tables can fit in memory at once, then you wouldn't have to go to disk as many times if you use that table for the inner loop.
Exactly, yes. So if one of them is small enough to fit in memory, then that one should be the inner loop. So this is kind of the same idea as kind of caching. Yeah, if you can rearrange your computation so that parts of it fit in the cache better, then it's going to be a lot faster. So let's assume now that memory is big enough to hold all of S. We definitely want S to be on the inside. And the DBMS is smart enough to load all of S and keep it cached and not let any of the R pages evict it. So now you only have to load S once, and you only have to load the R pages once. Okay, so we're using R and S. These are kind of just placeholder for some relations. Turns out we will always use R to refer to the outer relation and S to refer to the inner relation. The real relation is going to be something like games and events or players. I've written my query, so it's games join events. That implies that like games would be the outer loop. But no, the DBMS is going to decide which of these becomes R and which of them becomes S. So which of them is outer and which of them is inner. And if it knows, for example, that one of them fits in memory, then it will always pick that one to be S. Okay, so some notation now, just simple little symbols here. So R is the outer relation. P sub R is the number of pages in R. Similarly for S and P sub S. So then in the worst case, where you can't really, where you're just like thrashing in memory, as we saw, the worst case is number of rows in R times number of pages in S plus number of pages in R. This is in terms of page loads, not in terms of algorithmic computation. The best case is just load every page once. So you have PS plus PR. And this best case happens when S fits in RAM. Okay? Similarly to like if you've taken 4400 or maybe even 3810, if you have a big problem that can't fit in cache and you have this issue where no matter what you do, you can't rearrange the algorithm so that it's linear access. You have to skip around pages. You can rearrange the algorithm so that you work on smaller parts at a time and keep as much of it in memory as you can for as long as you can. And the DBMS will do that. So it's not that it can only ever get any advantage if all of S fits in RAM. It can rearrange it slightly so that it kind of reworks on smaller parts of the problem while holding other pages in memory. Yes?
So when we write our loops, does it matter which one we put as the outer or inner loop, or does the DBMS just do that for us?
Yeah, so when you write your joins like this, games join events versus events join games, the DBMS is always has power to choose which one becomes R and which one becomes S. Where it might matter is if it doesn't have enough information about games and events. But it usually does. So the answer to your question is almost always no. It doesn't matter what order you put them in your join. Okay.
But for best practices, like should the game join event against the DBMS loop?
For best practice, you should write it in the way that's easiest to read. Yeah. Okay, so this has all been ignoring indexes. Full cross products for everything in R, for everything in S. What if though? What if one of them does have an index on whatever column you're joining on? So only one of them has an index, not both. So in our example, let's go look at the actual query. Didn't realize it was this far back. Okay. Games join events on where the EIDs match. So I know EID is primary key in events. Pretend it's not. Pretend this is some arbitrary column. So they both have some column named EID. One of them has an index on EID. So should it put the one with the index, should it be R or should it be S? So intuitively S, because it'd be less expensive to reload it, because the index kind of lets you get there in fewer pages or something like that. Yeah. So it should be S. The one with the index should be the inner one. So it turns out there's an even better reason, though. What is, if the index is the one on R, what is that going to do for us? So, yeah.
It doesn't really do anything because we have to do a linear traversal.
It doesn't do anything because we have to look at everything in R anyway. We're not filtering, we're not looking for a specific thing from R. We're looking at every single R. So an index doesn't help. This is basically what the code looks like now. We have, so pretend R is an array, and pretend S is now a data structure, like a tree. You can't do an iteration, a more efficient iteration on a tree. An iteration is still an iteration. So we iterate over R, and then for everything in R, we do a fast lookup, an index lookup on S. And now it's not really a nested loop anymore. It's it's more like an n log n sort of loop instead of an n squared loop. It is, you kind of think of it as a loop because index lookup is going to be some loop-like algorithm, but it's going to be logarithmic instead of linear. Okay, so the index doesn't do anything on the outer loop, so you might as well put the one with the index on the inside. If you have the index on the outside, it doesn't change the calculus at all. It's still number of rows in R times number of pages in S plus pages in R. If you do have an index, now that pages in S term becomes log of pages in S, which goes way down. You want to look for each row in R that matches something with that same key in S. Yep.
Oh, so you're not doing a full join on it.
Right, so this is not a full cross product join. No index would ever help there. This is a join on some condition. Yeah. Okay, what if both relations have an index? We're only going to use the index on the inner loop, on the inner relation. Okay, so R versus S, whatever one becomes S, we're going to use that index. We cannot use the R index. So then, does it matter which one we pick to be R and which one we pick to be S? So here's the equation for the cost. So this is always showing as R and S, but pretend we have two options, events and games. Does events become R or does games become R? Does it matter? When would it matter? Yep.
I get the smaller ones on the outside this time. That would be better.
Okay, so this time you put the smaller one on the outside because this logarithmic term is going to have a higher impact on a larger table. Right? You get more win out of this logarithmic reduction for a giant table than you do for a small table. Okay? If you just take this equation and plug it in for some larger value and some smaller value, you will see that it's better if the larger value is the one corresponding to the one on the inside. So does that mean you have to keep track of which one's larger and smaller? The database system does. You as a user don't. The database system does. But we do still need to know how it's doing all of this stuff in order to understand when a certain query is not performing the way we expect it to. We need to be able to investigate why. Okay. And then finally, so that's kind of just the basics of joining. We're looking only at nested loop joins. Different rules based on which one's bigger, which one's smaller, and in combination with which ones have indexes. Okay, but then what if we have a multi-join? So, A join B join C on some conditions. So not cross-product joins, but theta joins. Lots of ways we could arrange this computation. So this is essentially now a triple nested for loop instead of a double nested for loop. Which one do I put on the outside, in the middle, in the inside? And we called the inside one T now. So R, S, and T. We could have A, B, C, A, C, B, B, C, A. It's basically going to use the same rules. If one of these fits entirely in memory, it's going to want to make that one be T. It's going to want to make it on the innermost. Okay, so I'm going to have a couple exercises for you coming up. One of them will be on the library. It'll be joining these three tables. The only way that these tables can join is ISBN going from title to inventory and serial going from inventory to checked out. So just kind of remember that. Those are the foreign keys that allow us to get around these tables. And assume it's not doing any smart page tiling like we talked about. And there are no indexes, even on the primary key. There would be, but pretend there isn't, unless the exercise says that there's an index there. Okay? So, question for you. So this is the exercise. Two problems here. And a lot of details here, so we'll kind of go over it first, and then we'll give you some time. So which one becomes the outermost, the innermost, the middle, and the innermost? So I have, just select everything, select something, doesn't really matter. From titles, natural join inventory, natural join checked out. Okay? And then we have some assumptions here. So 50,000 titles occupying 1,000 pages. 100,000 inventories occupying 100 pages. 500 checked out, all in one page. And our memory system can only hold 3 pages. So one from each, basically. So 2 questions. What will RS, and T be for the case where there are no indexes at all? And what will RS and T be for the case where there's an index on titles.serial? Okay? So take a few minutes with the people around you, work this out. Yep.
I said that inventory, yes.
Okay, so the other option is maybe swap those two. Yeah. With the information given, where it's not doing any smart tiling and only 3 pages fit, these two won't make much difference. But the DBMS is generally going to try to put the smaller one on the inside. So it probably would actually be the other way around. R would probably be titles, and S would probably be inventory. Smaller in terms of pages, not smaller in terms of rows.
In that case, why did we check out
It wants to put the smaller one on the inside.
Sorry, was it on the outside?
R is the outside.
Okay.
It's definitely going to put checked out on the inside since it's only 1 page. Okay, what about number 2? How does this index change things?
That titles is R.
Yeah, so that would be sorry, I take it back. It would not.
Titles is R, and then checked out is S.
Titles as R,
Sorry,
checked.
Titles as T.
Titles as T.
And then
Titles as T, checked out as S. Okay, so yes, it's definitely going to take. It's going to take titles and prefer to move it inward. Whether it would put it into the innermost or the middle. In this case, since checked out fits all in 1 page, won't make as big a difference. Turns out it's still going to be better. So every lookup into titles is still going to be possibly multi-page. Even though there's an index on it, it's not going to be 1,000 pages. It's probably going to be like 3 pages or something. So every index on titles is still going to be multi-page. So you'd want that one in the middle and still want checked out in the innermost. So it would be R equals inventory, S equals titles, and T equals checked out. Okay. Yep.
So you said for the first one that it's not that much of a difference to switch out of inventory.
For the first one, it's not a difference here because I'm saying memory only holds 3 pages. If, in general, memory is going to be bigger than that, and the best guess is try to put the smaller one on the inside. So it would, I'll just write it, instead of writing it in the way that doesn't matter, I'll write what it would probably actually do. R would be titles, S would be inventory.
Doesn't that still make a pretty big difference? Because you only load every page of titles once.
You're going to only load every page in titles once.
And then multiply that by all the pages in inventory.
Right. Okay. Another exercise. So this time, we're not picking what R, S, and T are. We get one index, one column to put an index on. It's a slightly more interesting query. So players join games, natural join events. So games and events can be natural joined on the event ID. And then we're joining where PID equals white player and date equals some certain date. So basically we want to know who are all the people that played as white on this date. Okay. Assume that games is larger than players and players is larger than events in terms of number of rows. Also assume that these rows from each table are roughly the same size. So number of rows is proportional to the number of pages for each of these tables. And we do have some indexes now. We have the primary key index on each of these. So we have EID, PID, and GID. Okay. So you get to pick one column to add an index. Which one will have the greatest impact? So turns out it's going to take some thought. So we'll actually take a few minutes here, work it out again with people around you. Games.whiteplayer. Okay, so what that lets us do is we're trying to join players and games. We don't currently have an index that helps with that. If we put it on games.whiteplayer, then our outer loop could be players. And then for each player, we could take the PID and go quickly look up the white player to find that match. This would cut it down a lot. So this helps with that loop a lot.
An index on games.eid.
Okay, games.eid. Which is kind of along the same lines. This is helping with the join. So this is going to do something like events on the outside. That's an E. Then for every event, we can very quickly find the game associated with it. So I'm really glad the first two suggestions were not to put an index on date, which is the obvious thing, I think, which definitely would help. But based on these sizes that I gave, so if you have an index on date, the first thing you can do, even before starting joining, is you can filter down to a very few number of events. Then you'd still have to multiply those few events by every single game. So these two indexes, which of them is expected to be better? And why would you argue that? So, Scott, do you want to argue why why did you pick that instead of games without white players?
So games have a greater magnitude than players, and events have a smaller magnitude. So events is going to repeat fewer times on a log of a greater thing.
Yep.
And then that is combined with, you have to have somebody be the outer loop.
Yep.
So players is the choice that I made.
Yep. So basically, you choose based on sizes. Turning which number into log of that number is going to have a greater impact. So we'll actually see after this, we can look at which one is actually going to be faster. We can actually we can have SQL tell us the plan that it picked. And we'll do that, but let's take our 5-minute break first. And it will tell you what it thinks about that query. Like, what is the plan that it came up with? What kind of loops is it going to do? What index is it going to use and where? It gives you basically for each row in the app. So it's not going to run the query. It's going to give you some table that represents what it's going to do with the query. So that table has rows in it. Each row represents, for a join anyway, each row represents like R, then S, then T, then whatever. And each of those rows, so it's telling you which table it's going to work with in what order. And then each of those has lots of columns about what it's going to do with that table. So it has an ID, meaning the ID of the select that operation came from. So if you have nested selects, they'll have different IDs. There are lots of them. We're pretty much only going to look at a couple of the most interesting ones. Key, so that will tell you basically which index it's using. And rows is going to be an estimate of the number of rows in that level of the loop. And it is an estimate. Like, it can't actually know that without actually doing the query some of the time. So let's take a look at that. I'm trying black text on white background for these dim projectors. Tell me what you think about that afterwards. So I have chess. I'm using like chess 3 just because we're going to mess with it a lot. It basically contains the same information as chess, except I've changed the tables a bit. I've stripped out foreign keys and I've stripped out indexes. The reason I stripped out foreign keys is because a foreign key automatically creates an index. I wanted to start with bare bones, so I'll do show index from games. It's messy, but the only one in there is the primary key. I can kind of fix this formatting. So there's only one row of index. It is the primary one. From events, only the primary key. From players, only the primary key. Okay, and then I have, in this text file, I have some queries here that we're going to play around with. Here's the one we had from the slide that you just did on that exercise. So I have explain, and then that query. Just find, players who played white on that date. let's use this formatting. Okay. So the first row in my output says the table is going to be games. So that's R. Then players, then events. Let's look at this. So not using any key on the outer loop, using the primary key on players. So it started with games, which is going to tell you who the white player and black player is. So it can take, part of my query is joining white player with player ID. So it's using primary key from players. That's why it put them in this order, games, then players. And then events. Okay, because it knows the event ID from what it just joined games and players. It can then go and quickly look up an event. Let's look though at the rows. So I have 11,000 roughly rows in the outer loop, 1 in the inner loop, and in the middle loop, and 1 in the inner loop because of keys. So it has to look through every game, and then it can quickly find the player, and then it can quickly find the event. If I put create index date on events date. So this is kind of like the obvious. Let's go back and look at the query. I'm searching by an exact date. So if I put an index on that, I can quickly just, remember the plan diagrams I showed? It could go and do the filter first, filter out all of the events, then do only a join on those events. So let's try that first, and then explain the query. So now we get events first, because it's actually just going to do like a pre-filter process. And look at this right here. This is another piece of information it's telling us, is this is actually not really part of the loop. It's not going to dynamically look up these events. This is a pre-filtered thing. So it's a const. It figures out all of the events on that date first. Then it goes and does the rest of the joins. So roughly 3 rows, it thinks. And then we still have like 11,000 rows of games and 1 row of players. Okay, let me drop that.
So sorry, is that actually 4 rows?
It looks like it's touching more rows. It is actually going to be a little faster. You have to remember these are estimates. But yes, I mean, the point is that's actually not going to help all that much, is that index. So let's try now, let's create an index on, let's call it EID, on games EID. And then explain the query again. Okay, now it's putting events first again. So remember, the very first, with no indexes, it was doing games first, and then, I believe, now it's doing events first with an estimate of 6,000 or 7,000 rows. Then games with an estimate of 1 row. Then players with an estimate of 1 row. So we've dropped it from 10,000 to about 6,000 or 7,000, and it rearranged what R and S and T are. Okay. So any questions here? All right. Have another query here. find all opponents of Magnus Carlsen. This was one of the problems on homework like 3 and 4. The original query came from 3, and then you wrote an SQL version of it in homework 4. We have a few options here. I know these are like long queries. Let's kind of just look at one of these. So this first one, I have a comment here that it's using a self-join. So I do players P1 join players P2. I'm basically doing this in order to avoid a union. So I'm taking a full self-join of the players table, where the column on the left will be every other player except Magnus Carlsen, and then the column on the right will be Magnus Carlsen. So I'm basically making a table that matches Magnus Carlsen to every possible opponent. Not all actual opponents, but every possible opponent. And then we'll filter it down from there, where those two people were actually in a game together. So that's where the rest of this stuff comes in. So this is where I'm saying, the opponent is white and Magnus Carlsen is black, or Magnus Carlsen is white and the opponent is black. So let's try that query. Oh, what index did I just make? EID, let me drop that. And then we'll paste in this big self-join to find all of Magnus Carlsen's opponents. So it's going to start with P1, that's the renamed players. 8,000-ish rows. And it's going to go to G, which is renamed games, 11,000-ish rows, and then players again, same number of rows. So like 8,000 times 11,000 times 8,000, lots of rows visited. One obvious thing we can do to help this query is find Magnus Carlsen quickly. That's by name. All I've specified is his name. Okay, and so we get a const. This is just going to make P2. It's going to take P2, immediately find Magnus Carlsen, and then it has to join that with P1 to find all potential opponents of Magnus Carlsen. And then it has to take that whole thing and join it with all of the games. So we did, a little better. Let's go back and look at the query again. So I have like some comparisons using white player, comparisons using black player. So maybe add some indexes on those. Okay, we'll do both. And it looks about the same. So we have 1 times 5,000-ish times 11,000-ish. Didn't really help, just because, so look at this part of the query. This is where I have some complex logic in here. I have P1 equals white player and P2 equals black player, and then I have this OR in there. All this stuff, you might think like, well, couldn't it do something smart where it could go, like it knows who the white player is, it could go and quickly look that up, or it knows the player's name, it could go and quickly look up white player. But this complex logic here is basically just throwing it all off, and it still has to just do these nested loops, and those two keys end up not really helping. Was there a question over there?
I was going to ask if you had removed the index on name, but it sounds like you didn't.
I did not remove the index on name. Okay, so indexes that we thought might help didn't. Here's another query, returning the same, functionally the same query. It's also using kind of this self-join method, but it's written differently. So I know it's a lot of text here to look at, but kind of look at some main differences. There's some nested selects in here. So kind of still written differently, but I've always said that the way that you write your queries shouldn't matter. The plan generator will figure it out. So let's paste that one in. So, and we get 1 times 11,000 times 8,000. It was like 5,000 times 11,000 before. But remember, those are estimates. This is roughly looking to be the same. It did actually pick a different plan, but the cost of those plans is going to be similar. So here is where I've lied to you about it doesn't matter how you write your queries. Here's one using a union, where what it's going to do is just find all the games where Magnus Carlsen played as white and select the black player. Then find all the games where Magnus Carlsen played as black and select the white player. Then union those together. That's even kind of a more natural way of thinking about it. So paste that in. We get more steps. So constant step, constant step, constant step, constant step, union constant step, which it's not going to be. It's estimated to be constant. It's going to be small-ish, like 10 things unioned with 10 things. But it's way cheaper. So let's think about the way that we're doing these queries. Let me just highlight part of this query. Right here. Highlight this part. Players join games, a little more. Players join games where name equals Carlsen and white player equals PID. This query is going to be extremely fast given the indexes we have. Okay, we have an index on name. It can immediately find Magnus Carlsen. And then we can take his PID and go find white player in the game statements. Here is the other part where it's basically the opposite condition. Still looking for Magnus Carlsen, but then looking for where he played as black. Those two should be pretty easy to see. Those are going to be very fast. Then all we have to do is union them together. So it is capable, if I'm using different primitives to describe my query, like union versus self-join, turns out that can actually make a big difference. The plan generator is not smart enough to turn this into a union of 2 individual separate selects.
So is an index like a grid line? Because like an index on white player, we find all the rows in that white player.
Is an index like a group by? Yeah, I mean, as part of executing this query, it will find all of the ones that match. But it's not a group by. I mean, it will find all of them if there are more than one. But the index helps it find all of them very quickly. It's saying constant time, but that again is just an estimate. It's guessing that after picking out Magnus Carlsen, it's guessing that the number of games he played in is roughly constant. And it is. It's like 20. Okay? So just kind of recap. We saw with this, with a certain query where we're looking for white players on a certain date, we get these 2 different plans. Games, players, then events versus events, games, then players. and the estimate amount of work went down. So just kind of wrap up a few additional things here that I've glossed over. Turns out MySQL automatically creates an index on any column that's a foreign key, because the assumption is you're going to be using that foreign key in a join operation. Otherwise, why would it be a foreign key? Other than for data integrity purposes. But so if you want a foreign key for those reasons, but you're not actually going to be joining on that column, then unfortunately you actually just have to not make it a foreign key. Like you can't have both. Or just make it a foreign key and accept that there's going to be an index there, even if you never use the index. It'll take up some space. Okay, so us as MySQL developers, as users of MySQL, what we need to think about is like what join operations is our query going to do, and are those joins going to be fast, and are there keys I can add that will help it? If you're not sure, use explain. So if you use explain and it's like not using some index that you thought it should use, then that'll kind of help you realize what's wrong with your query or how to kind of reformulate your query. There are ways to write a bad SQL query that will prevent the plan generator from picking the best plan. So as we just saw, we did this weird like self-join thing with two filters ORed together versus two individual selects with filters, union them together. Ended up being way faster, like constant versus cubic or squared. Okay, that is it for today. See you next time.